Well, guys, first things first. We've got some homework that we need to look at. And frankly, I don't remember on Monday if any of you were gone. Does anybody need homework packets because you weren't here last time? You guys are all good? Okay. So, guys, grab your homework packets. Let's go over these. If there are not questions on today's homework, it's because you're not really paying attention. Because, guys, there's a ton of stuff on this homework assignment that we did not talk about in class, which doesn't mean that's unfair or wrong. It just means we need to talk. So, guys, I'll let you, we'll see. I may lead the charge at first. Well, let me lead it first. And then, guys, if you have additional questions, certainly we can do that. Remember, guys, this is our last unit. We're still recording homework online. Make sure you do this before midnight tonight. So, guys, if you'd allow me to sort of drive the process at first, again, lots of questions. So, question number 1 says, list characteristics for acids and bases. Guys, that's kind of like saying, describe the sky. There's 11,000 different things that you could have written down. So frankly, what I did is I just wrote down some things that maybe you didn't know. There are probably other things that you pulled out of what we talked about last time. But guys, I just wrote down some things that maybe you didn't know. Like acids are sour and bases are bitter. They're both electrolytes, which means when they dissolve in water, the solution conducts electricity. Acids react with metals to form hydrogen. We found that out when we made the hydrogen and blew it up a couple labs ago. Bases are very slippery. Most soaps are basic. And then, guys, finally, we talked about indicators. We did the indicator lab, and they cause indicators to change color. So those are what I put. Did you have other things that you put that you'd like to check to see if they're acceptable? You guys okay? Or did you just blindly write down what I did? All right, anyway. So then, guys, down below, these you've got to know for sure. Guys, I would put a big old star by number 2. You're going to see that for sure on the test. But in addition to that, guys, also on the test, you need to be able to think through this idea. Guys, these, my board's not on. These two definitions right here are the same. We talked about that in class last time. But guys, you've got to be conceptually clear on the idea that Arrhenius said acids are hydrogen ion donors, and then Bronsted-Lowry said they're proton donors, but hydrogen ions are protons, therefore those are the same. And then guys, the base definitions are different. Arrhenius says gives away OH, and Bronsted-Lowry says takes in protons. You guys good to there? Okay, then guys, looking at question number 3, you need to know just simply what hydrogen and hydronium are. Yeah?
Question about the whole theory question.
Yeah?
If we know that Arrhenius is not correct, why do we say not?
It's not that it's not correct, it's that it's too narrow. And so actually, I know I say this more and more and I shouldn't. In AP next year, we actually, when we talk about acids and bases, for at least half the year, we just use the Arrhenius definition. It's good enough through Christmas, and then after Christmas, we've got to bring in Bronsted-Lowry. So really, the Arrhenius definition is not wrong, it's just narrow. But the reason, Sam, that it actually works is this. We talked about this a little bit last time, but if you put something like NH3 in water, NH3 is basic, but it doesn't contain OH. But what it does is it reacts with water and it pulls off a hydrogen and it makes NH4 and then it makes hydroxide. So it turns out that in water, so if this is in water, then the Bronsted-Lowry and the Arrhenius definition are also the same, because what these Bronsted-Lowry bases do is take a proton off of water, and that leaves OH, which gets us back here. Is that okay? Okay. All right. So guys, let's keep going. Moving down a little bit more. So guys, amphoteric, you needed to know the definition. Then guys, down at the bottom, these are terms that we did not talk about. But that's okay, because you should have been able to figure out what they mean by either Googling them or looking at the answers. So guys, looking at the answers, we'll start there. You'll notice that this is a decomposition reaction, and this is a decomposition reaction. So what do dissociate and ionize mean? And guys, the answer is simply to break apart. So what we're looking at is how these things break apart, and those are the balanced equations. You guys good there? Yeah. Great. Oh my gosh, Jessica, that's a brilliant question. So down here in letter B, why is the hydrogen not H2? And the answer is because it's dissolved in water. So the question then becomes, where does this happen? Where does nitric acid break into hydrogen ion and nitrate ion? And the answer is in water. And in water, hydrogen ion is stable. It doesn't have to bond with another hydrogen to form H2. So now the question is why? What is it that stabilizes the hydrogen? You ready for the answer? Turn the page. This is actually why this works. If you look at the next page, this is actually what HNO3 does. So the HNO3, the nitric acid, when it breaks apart, it gives that hydrogen to water and it forms hydronium ion. And so that's actually what's going on, is that hydrogen doesn't have to bond to another hydrogen because it bonds to water in order to form H3O, and that's what stabilizes it. Honestly, in acid-base chemistry, it always stays by itself, because all acid-base chemistry, at least until your junior year in college, happens in water. So you always assume that the hydrogen is okay by itself. Yeah, go ahead, Ellie. Yeah, that's, again, I'm so sorry for saying this all the time. In AP, we talk about that a lot. I'll give you the answer, but you don't need to worry about it. So the answer is you include water only when you have to. So what we find in AP is that we want to write these equations as simply as we possibly can. And the simplest way to write these is without the water. Sometimes we have to include the water, and then we do, but otherwise we don't worry about it. But just trust me, I'm not going to put you in that spot like on the test or anything like that. So guys, you good on these? We're good? All right. So then, guys, moving down, this is a different way to ask you to figure out acids and bases. So you're looking over here to the left, and you're asking yourself, which is the acid? We're figuring that out by figuring out who loses hydrogen. So cover over the hydrogen here. What's left is NO3. That is NO3. Therefore, we know that's our acid. The other is the base. Guys, this is a skill you got to have. I'd put a big old star by number 7. You're going to see that dude for sure on the test as well. So, guys, questions on 7? You okay? Okay, then moving down to number 8, here's where we start talking about conjugates. So guys, again, the idea is to figure out your conjugates, go to the acid, take away a hydrogen. What's left is the conjugate base. But also notice the charge, you guys. When you pull a proton off of a molecule, its charge goes down by 1. So it's negative charges for your conjugate bases. Is that okay? Okay. Then guys, moving on again from there to number 9, you need to be able to figure out conjugate acids and bases. Conjugate bases, you take away a hydrogen, charge goes down by 1. Conjugate acids, you add a hydrogen and the charge goes up by 1. Notice on this one, guys, you could have taken away 1 or 2 hydrogens and either one's fine. So questions on those? You're okay there? Okay. So then, guys, moving to the next page, this is the way you learned this in class. The idea is figure out which one is losing the hydrogen. That's your acid. The minute you know that, the other one is your base. Then once you figure that out, to figure out your conjugates, go to the acid, take away the hydrogen, whatever's left is the conjugate base, and then the other one's your conjugate acid. Then, guys, down at the bottom in number 12, this is talking about the H2PO4 ion. This thing is amphoteric. So in this example, it turns into H3PO4, so it took in a hydrogen, it's a base. Here it turns into HPO4, so it lost a hydrogen, and that makes it an acid. And then guys, finally this, down below, I know we did this hurriedly at the end of the day, but guys, you got to be able to do this math. The equations will be given to you on the test, but you've got to be able to solve these and come up with these answers. So there's obviously lots of practice here. It's really between you and your calculator to make sure that you can run these numbers and get these answers. So if you're not able to do that, let me know. I'd be happy to help you with your calculators. So guys, we just went through every single problem. Other questions on the homework? You guys okay? Before midnight tonight, you'll record it? Yeah? Okay. So anything else you want to talk about here? All right, so guys, grab something you can take notes with and on, and we're going to talk calendar for a minute. And then we're going to dig into some interesting stuff. All right, so Kyle is still gone. Riley is gone. Close this. Get rid of this. Grab this. Oh my gosh, you guys, we're almost out of April. Where did it go? Hey, so guys, as we're getting ready, I got a flood of emails on Wednesday. So if it was you, first of all, I wrote you back. But if it was you, I'm sorry, and thank you for letting me know. Guys, I got a flood of emails yesterday with people saying, oh my gosh, Mr. Knappenberger, I thought the replacement test was on Thursday, and now I see it's on Tuesday, and I missed it. And I'm like, what are you talking about? It's always been on Thursday. Guys, the mistake that I made is accidentally this part said Tuesday. Guys, if you saw that, I'm so sorry. We decided to push the test back to Thursday, but I had already put it as Tuesday here, and I forgot to change it. You're fine. The test is today. You didn't miss it, and sorry if that caused you undue concern. So guys, please remember the replacement test is after school today. And then guys, moving forward and looking at the rest of the unit, today we're going to talk about what makes reactions go faster or slower. Then guys, when we get together next week, we're going to go into lab and do a lab where you make reactions go faster. Guys, if you're not going to be here for the lab on Monday, you're going to need to go to the grocery store before you do the makeup lab, because you're actually going to do the makeup lab at home. You're not going to watch a video of it. You're actually going to do it at home, and you need to go shopping. Then guys, Thursday and the following Monday are 2 days that go together talking about a thing called equilibrium. Then we do another lab on the 13th, then our last new material on the 17th, then the test is the 20th. And guys, this is new to the calendar. Your class period on the 20th will be the deadline for all late labs and late homework for that unit. So guys, we are going to give you until the very last day of the quarter for you to turn in late lab work. So that'll be on the 20th, so keep that in mind there. So questions about the calendar? You guys all good? Yeah?
With the assignment on the 17th,
Yeah.
does that mean that it's open until the 20th?
Yeah, exactly. And so we're not changing the rules at all. So the window for all late homework will be midnight that night. Yeah, so we'll close that. And that's true not just for this assignment, but as it's always been, all the late homework for the unit. So guys, questions about this? You guys good? Do remember this. I'm going to be gone on Thursday the 6th and on Monday the 10th. I'm going to be in Denver at a volleyball tournament. You will be watching the screencast for those 2 days. It works great. Everything will be fine. We'll make allowances for turning in homework relative to that. So guys, basically these two homework assignments, you won't be turning in until I see you on the 13th so that you can actually get your questions answered. I don't want to change the calendar because it can, wait, I can. I'll just change this to indicate that it's due on the 13th because both of those assignments will then be due when I get back. So, guys, anything here? You guys good? All right. So guys, grab some note-taking stuff. Let's get started. This is good stuff. You're going to like this. Yeah? Oh. Hold on a second. Did I miss? Hold on. Let me think through that with you. So we're talking about the rate lab. I mean, you could turn it into the sub. But I know that, I don't know. I guess I'm fine waiting. That's fine. Yeah. I mean, what I was thinking is you could turn it into the sub, and I'm here Tuesday and Wednesday if you needed to go over it with me. But I'm fine pushing it back, too. Would that be better? Yeah, let's talk on Monday. Remind me on Monday. You guys good? All right. So, guys, again, today what we're going to do is we are going to talk about what makes reactions go faster. The date today is the 29th. And guys, the topic today is reaction rates. So guys, you've been in this class long enough to know that Thursday relies upon Monday, and Monday relies upon the previous Thursday, and material always builds on itself, right? Guys, that is not true today. The stuff that you're going to learn today has absolutely nothing to do with acids and bases until we get together next week, and then it has everything to do with acids and bases. So guys, you're going to learn reaction rates today as a standalone concept, and then we're going to marry these ideas together, acids and bases and reaction rate, but we're not going to do that until next week. So guys, let me lay out for you how today is going to go. So the very first thing we need to do is I need to share with you 3 terms, and we need to define them. So you're just going to blindly write them down. There are 3 terms that you need to know. Then, guys, we're going to talk about what is it that determines how fast a reaction goes. Then once you understand that, we're then going to figure out how to make them go faster. And then that leads into what you're going to do in lab next week. So terms, what determines how fast a reaction goes, and then how do you make them go faster? You guys ready? Terms first, write them down. So guys, the first term that you need to know the definition for is the term magnitude. You cannot write up next time's lab without using the word magnitude. So guys, what does the word magnitude mean? And the answer is simply the amount of energy that an event possesses. So guys, when we talk about magnitude, we are going to talk about the magnitude of collisions. So these are low magnitude collisions. These are high magnitude collisions. So guys, it literally means how hard are things running into each other. You can have low magnitude and high magnitude collisions, and it simply means how much energy is involved in the collision. Number 2, frequency. This one you probably know. It's how often an event occurs. So this is a low frequency collision, and this is a high frequency collision. You guys good on those? Pretty straightforward. They're important though. And then guys, finally, the last term that you need to know is reaction rate. That's what we're studying today. How do we make the rate of a reaction go up? Well, in order to figure that out, we need to know what that is. And it's actually the speed that a reaction progresses. It would never end a sentence in a preposition. It is the speed at which a reaction, how did I say it? I did. The speed at which a reaction progresses. Do they still talk about that in English? Never end a sentence in a preposition. Remember English, second floor, Mr. Ellingford's snazzy dresser? Never mind. Jekyll and Hyde. All right. All right, so guys, let me give you the units. So how do we measure the speed of a reaction? Well, there you already know that we measure speed in units that are fractions, like the speed of your car is miles per hour. Well, guys, for reactions, we actually measure the speed in moles per second. How many moles of reactant get created in a second of time? Those are our units for reaction rate. All right. So guys, here then is where we are, and now we're going to actually start doing some thinking. We know that magnitude is how hard, we know that frequency is how often, and we know that reaction rate is how quick a reaction goes, measured in moles per second. You guys good? You okay? All right. So guys, what we're going to do is we are going to bookend the day. I am going to introduce you to two chemical reactions. We're going to start the day by talking about it, and then we're going to ask a question that we don't know the answer to. Then at the end of the day, we're going to ask the same question, and magically, you're going to know the answer. So guys, the question is this. Here we have a fire in a fireplace, right? Here we have an iron ring nailed to the side of a centuries-old barn sitting there rusting. Guys, here's the question that I have for you. What do these two processes have in common? What do these two processes have in common? Talk to the person next to you about it for a second. What do they have in common? Fire. Fire. It's fire. It's got to be fire. All right, guys, let's talk about it. Isaac, I think I saw you throw up a hand. Yeah? Yes? Go for it. What did you got? Okay, guys, let's call a timeout right there. Let's take these slow. So, guys, both of these are reactions with oxygen. So, you all know from being Boy Scouts that in order to get fire to burn, it's combustion. Well, sort of. It's not a hydrocarbon. But, guys, we need oxygen. But you probably also know that rusting requires oxygen. Because, guys, this is not what that ring looked like when the farmer nailed it to the side of his barn 200 years ago. But over time, it's been rusting. And rusting is a reaction with oxygen. So good. Number one, they both involve oxygen. What else do they have in common? Did any of you get past that, Tori? Beautiful. So these are processes over time. So let's talk about what's going to happen as we go through time. So guys, imagine if we could take this picture, put it away, and come back a day later. What's this going to look like? Done, right? Ashes. Guys, what's this going to look like? Kind of like that, right? If we could do a time lapse, we know that over time it's rusting more and more and more, but it would look a lot the same one day to the next. So what does that tell us? Well, it tells us reaction rate. Which one's reacting faster? Obviously the fire. So guys, what else? Other observations? Yeah? I love that. Yeah, so both of them are taking their reactants and chewing away at them, right? They're not truly decomposition reactions, but I absolutely love that. Because what else? Let me share one with you then. Ready? They're both exothermic. Did you know that? So guys, clearly the one on the left is exothermic, right? Because that's why we light fires. We want to warm up by the fire. But guys, did you know that rusting is also exothermic? The answer is yes, I knew that rusting was exothermic. Because guys, have you ever seen those little packets that you can buy at Walmart that are the heat packs that you can shove in your gloves and they warm up your hands? Guys, what is inside of one of those heat packs? And the answer is iron ground up as a really fine powder, and there's an accelerant in there. And when you pull that pack open, what you're doing is you're exposing that package to air. And all it does is it takes the iron filings inside of that packet and they rust. But it's going a lot faster because there's an accelerant in there. And actually the heat that warms up your hands is the heat that is released from rusting iron. Guys, it's exactly the same reaction as this. It's just sped up a little bit. But guys, all rusting processes are also exothermic. Yeah? So here's what we know. We know they both involve oxygen. We know they're both chewing away at the reactants. And now we also know they're both exothermic. But guys, based upon what Tori said, we also know they're not going the same speed, right? The one on the left going like crazy, the one on the right going really slow. Are we all in agreement on these ideas? Okay, so guys, this is the question then that we are not ready to answer, but we are going to develop the answer. Guys, why does this go so fast and why does that go so slow? And I ask that question completely rhetorically because we don't know, but we will know in about 20 minutes. You guys ready to get into this? So here then is the question that we are going to ask and answer. What has to occur for a reaction to take place, whether it's fast or slow? So the question that we're asking is, why is one faster than the other? But in order to answer that, the first thing we've really got to understand is this. What has to happen for a reaction to take place fast or slow? And guys, this is where you want to start taking notes. Again. So what has to happen in order for a reaction to take place, regardless of how fast it's going? Well, guys, you ready for the simple answer? The answer is this. There has to be collisions. In order for wood to react with the oxygen in the air, they have to, is this annoying? They have to run into each other. And guys, in order for iron to react with oxygen and rust, they have to run into each other. It sounds simple, but it actually has a name. Guys, it's called the collision theory of reaction rates. That's what you want to write down. This is what is called the collision theory of reaction rates. And guys, it really is this straightforward. For a reaction to occur, the reactants have got to collide. The oxygen has got to run into the wood. The oxygen has got to run into the iron. And if they don't run into each other, there's no reaction. But guys, if it was really that simple, rusting and burning would happen at the same speed because they're all running into each other. So what does this have to do with speed? And guys, the answer is this. It's not just enough for them to run into each other. They've got to run into each other with enough energy to break the bonds into reactants. And once those bonds are broken, they can now turn into products. So guys, when they run into each other, they've got to hit with enough energy so that the bonds inside the reactants break apart. And at that point, they can then turn into products. So guys, this may be the world's dumbest analogy, but try this on for size. Imagine that you're out in the parking lot here at Orem High, right after school, and two cars gently bump into each other, and then they bounce off and go their own way. Well, guys, both of those cars are unchanged. They tapped and they drove away, and you'd never know they even ran into each other. Now, guys, imagine that you're on I-15 and there are two cars going 90 miles an hour and they hit head to head. What's going to happen? This is weird, but bear with me. What's going to happen? Well, guys, both of those cars just explode. They hit with so much energy that parts go everywhere. What that means is if you're good, you could show up and you could take all those parts and build two brand new cars. See what I'm saying? So guys, the idea is if they hit softly, they just bounce off and nothing changes. But if they hit hard, parts go everywhere. The bonds break, parts go everywhere, and you could gather up those parts and you could build different cars. Guys, that's exactly what's going on here. They've got to hit hard enough to make them things blow apart, and then you can reorganize them and turn them into different stuff. So guys, what this means then is that not all collisions are effective. If they don't hit hard enough, see where this is going? If they don't hit hard enough, nothing happens. If it's a touch of bumpers in the parking lot, nothing changes. If it's a big old head-on collision at high speeds, the cars blow apart, and you can put them back together in different ways. So guys, what then becomes the question? Say it again, Rat. How hard do they have to hit? And guys, the answer is different for every reaction. But guys, that's the question that we've got to ask. How hard do these things need to hit? Rhett, I can always count on you for the good answer. Is that wrong? Because then that means there are wrong answers in that anyway. I love it. So guys, do you see where we're going with this thought next? So how much energy then do these collisions have to have? Are we all caught up to that point so we can transfer into that thought? Is that okay? All right. So guys, how hard do they need to hit in order for the bonds to break and in order for a reaction to take place? Guys, I'm going to switch this slide. Is that okay? Guys, the answer to that question is activation energy. The next point in your notes. So let me just define it for you, and then I'll show it to you. So guys, activation energy is defined as the minimum amount of energy needed for a reaction to take place. Now guys, you can think of this as being a hump that exists between the reactants and the products. And if a collision can't get over the hump, nothing happens. So the more collisions that get over the hump, the faster the reaction goes. So guys, as you're writing this down, let's review. Not all reactions go the same speed. But regardless of how fast they go, there has to be collisions. But those collisions have got to be hard enough to break the bonds in the reactants and allow the reactants to reorganize. So how much energy does that take? And the answer is activation energy. That's the amount of energy that these collisions have got to have. It's like a hump between the reactants and the products. And the more collisions that get over the hump, the faster the reaction goes. You guys okay? I'll let you catch up. So give my board a second to connect. Come on, board. There we go. You guys good? Oh, Sam, go ahead.
So would that mean that fire is faster because it's got a less activation energy or less needed activation energy?
Maybe. We're actually going to draw that picture at the very end. You're exactly right. Yeah, that's it. All right, so guys, let's explore this idea of hump. And so yesterday, went for a bike ride, rode up South Fork, coming back down South Fork, right there on 800 North, and the putt-putt golf course on 800 North is now open for business. You know the one I mean? And guys, if you've ever played that putt-putt golf course, or any putt-putt golf course, you've all seen this hole, right? This is the pinnacle of humiliating, especially if you're on a date. Because guys, you know how this goes, right? You're trying to impress your date, you're trying to finesse the shot, you get up there, you hit the ball, tink, and you don't quite hit it hard enough. And guys, you know how the story goes. You hit the ball, but you don't hit it with enough energy, and it goes to there, and then what's it do? Rolls right back down to your feet as if nothing changed. So guys, in order to create a change, what we need to do is we got to hit this with enough energy that it gets to right there. Once it's there, it goes this way all on its own. But there has to be enough energy for it to get over the, see the connection, the hump. Now guys, what if this hump was lower? Less energy. What if the hump is higher? That'd be fun. Then guys, we need to work on this. This could be good. Then you gotta hit it with more energy, right? Well guys, reactions are exactly the same way. The higher the hump, the more energy that there's got to be in order to get over the hump. Does that make sense? Now guys, in science, we don't draw it like that. We draw it like this. And guys, you need to copy that into your notes. Make it about 4 inches by 4 inches. So when you draw this in your notes, here's what you're going to do. Draw a y-axis, draw an x-axis. The y-axis is energy. The x-axis is reaction progress. Then guys, draw a line about halfway up, label it reactants. Then move to the right and draw a line below it, label it products. And then guys, this is the hump. And label that activation energy. Guys, this is the way we think about this as chemists. Sorry again, I know I say this so much right now, but it's in AP. Guys, we draw these diagrams like almost daily. This is the way chemists visualize energy. So altitude, height is connected to, is analogous with energy. So we've got reactants, and if we want to turn them into products, the collision has got to get over the hump. And that's called activation energy. You guys okay? You done drawing? Not quite yet? So guys, let me clean up my mess. You guys okay? We're about to pull 1,000 ideas together, guys, right now. Go to the very top of your notes and read the definitions of frequency and magnitude. Reread the definitions for frequency and magnitude. You got them? Magnitude is how hard, frequency is how fast. Good? Now, guys, this. It says the more collisions that get over the hump, the faster the reaction will go. So now, guys, let's talk about this. If we have reactant A and reactant B, and if they have to collide to get over the hump, guys, when they collide, they've got to collide with that much energy to get over the hump. If they just bump into each other and don't have enough energy to get over the hump, no reaction happens. So guys, ready? What can we do to this reaction to make it more likely that the collisions get over the hump? Well, what do we need to do? We need to increase the magnitude of the collisions or the frequency of the collisions. Because guys, if the speed of the reaction is determined by how many collisions get over the hump, they either need to hit harder or they need to hit more often. And either one of those will get more collisions over the hump and the reaction goes faster. Does that idea make sense? Let's write it down. So guys, this then becomes the idea. For a reaction to happen, more collisions have got to get over the hump. So then the question is, how do we do this? How do we make more effective collisions? And guys, the answer is we either increase the magnitude of the collisions or we increase the frequency of the collision. See how that comes full circle? So guys, if we want more collisions to get over the hump, we either need harder collisions, magnitude, or we need more collisions, frequency. So now the $11,000 question is, how on earth do we practically do this? How do we make elements, atoms, compounds, whatever, wood and oxygen, metal, and how do we make things collide harder or more often? Rat. Good for you. Heat them up. Don't write these down. We're going to get into them one at a time. Guys, that's one of the things that we can do is heat them up. What else? What else can we do to a reaction to make them run into each other more often? Yeah. Yeah, actually, exactly. Surface area. We can grind them up. Guys, that's why if you have a big old chunk of something and you throw it in water, it doesn't dissolve like ice, right? If you have a block of ice and you throw it in water, it cools down the water pretty slowly. But if you have ground up ice, like pebble ice, besides being awesome, it also makes your drink colder faster because there's more surface area to interact. Great point. So guys, we've got heated up or grinded up. There's actually one more thing that you can do to make a reaction go faster. Yeah, Rhett? Concentration. That's it. You guys did it. We're done. But now we need to talk about it. Guys, those are them. There are three things that you can do to make a reaction go faster. Heat them up, grind them up, or get more stuff. Let's do them one at a time. You ready? So guys, first of all, temperature. Just write this down. Temperature. As the temperature goes up, the rate goes up. Guys, it's that simple. As the temperature goes up, the rate goes up. But guys, the $11,000 question is why? Why does just a second, I want to frame the question before we answer it. Guys, why does the rate go up when the temperature goes up? But guys, in order to answer the question, and these are the things you're going to have to think through on the lab next time, guys, it's one of two answers. It's either the frequency of the collisions or the magnitude of the collisions. The question is, which one is it? Just a second. In order to frame the question, guys, right? Oh, I like this. Hold on. So guys, in order to frame the question, I think we all know this, but let's be sure. In order to frame the question, we need to know the difference between hot and cold. So guys, how are hot things different than cold things? They move faster, right? So guys, cold is like a turtle. And hot is like a weird naked guy. So the idea here is hot is literally moving faster than cold. So guys, if hot is moving faster than cold, does that mean the frequency of the collisions go up? Or the magnitude, the energy of the collisions goes up? Okay, so let's see. So if we have two things that are moving slow, they're cold and they go bump, and they go bump, and they go bump. But if they're moving fast, they're going to run into each other all the time, right? So frequency goes up. But is that it? It also goes up. And this is the only one that double dips. I hate doing this, but anything for science, right? So guys, the idea is if you're moving slowly, when you do hit, it's like, not much energy, right? But if you're moving fast, it's like bam, 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 bam. It's tons of energy. So guys, this one actually double dips. It is not just the frequency of the collisions, it's also the magnitude of the collisions. You need to know that. It's frequency and magnitude. That's where we're scratching down. It's both. Oh man. The next slide that's about to come up makes me sad. You'll see why in a minute. You guys good on that? So Sam, you're exactly right. Rhett brought us to the idea that it's frequency, but Sam's right, it's also magnitude. If you're hotter, you're faster. If you're faster, it's higher, it's more collisions and harder collisions. It's all about kinetic energy if you've done physics. You guys good? Okay, so the second one that you came up with was Ellie with surface area. We're going to do that third. So who said more stuff? Was that Rhett? Rhett, you're on a roll. Guys, the next one's concentration. And let's just say it really simply. Guys, as the concentration goes up, the rate goes up. But again, guys, we know the real meat here is why. Is it frequency or is it magnitude? Frequency or magnitude of collisions? Well, guys, in order to paint the picture for you, what I'd like to do is show you a high and low concentration environment. Now, guys, I made these slides up 3 years ago. This is pre-COVID. So ready? A high concentration environment would be Cornhusker Stadium on a Saturday. Look, there's people in the stands. Remember that? Yeah, me neither, right? Yeah, vaguely. So, guys, sadly, this is more of our realities now. A low concentration environment. This is actually in Salt Lake City. This is a courtyard outside an office building during lunch up in Salt Lake. Sadly, we look at this and go, oh yeah, that's normal because they're all 6 feet apart, but you get the idea. So, guys, if we look at this environment, this is a low concentration environment. These people are moving around, but they're spread out. Over here, we've got a high concentration environment. Those people are moving, but they're tightly packed together. Where will we have more collisions? Go ahead, Ryan. Yeah, right. Because the chances of these people bumping into each other, even if they had their eyes closed and they weren't trying to avoid each other, pretty low, right? But guys, you can't go to a BYU football game when we actually get to go to BYU football game. You can't go to Cougar Stadium, Lavelle Edwards Stadium, and not just run into people. Because there's so many people packed into a small space that there's going to be a high, as you said, Ryan, frequency of collisions. Go ahead.
Another analogy is
Yeah?
if you're in a dance,
Yeah. Oh my gosh. Absolutely. Yeah, right. But that, or if you then go to a ballroom competition, right, they're not running into each other as much. Different dance. You guys get the idea? I love the analogy. So guys, that means then that frequency is the deal. And now we're all mourning the loss of spectator sports. Although I do actually have concert tickets for the summer, and they're really telling us it's going to happen. It's exciting. Chris Stapleton up in Boise, Idaho. All right, you guys good? All right, two more, but one more. So guys, Ellie brought up the idea of surface area. So guys, ready? As the surface area goes up, the reaction rate goes up. So guys, it used to be that this was an easier question to answer, but we can do it anyway. So again, the question is why, right? When surface area goes up, why does the rate go up? Is it a question of frequency or magnitude of collisions? Now that Boy Scouting is no longer a thing in Utah County, it's a little bit harder to have a connecting point on this. But guys, allow me, if you will, this analogy. So imagine that you want to light a fire, and you go out to the wood pile, and you stick a match underneath one of those logs. What are the chances that you're going to light a fire? In Utah County, really good, because all good scoutmasters douse everything in gasoline before they put the match to it. But, guys, understand that if it were not for gasoline, this is never going to light. So what do we need to do in order to start a fire? What do we need? We need kindling. So, guys, why does kindling light where logs don't, given that they're both made of wood? It's a question of surface area. So guys, the idea is if you take a log and if you measure its surface area, it's just the outside, right? But if you split the log, you have now exposed a new surface, and that surface oxygen can run into. And if you split it enough, you've created so much surface area that now there's all sorts of places where the oxygen and the wood fibers can get together, and now it burns. Now, guys, does that mean that they're hitting harder, or does that mean they're hitting more often? Which one? More often. Guys, it doesn't mean they're hitting harder. They aren't moving any faster, but they are hitting more often because there's more places for them to hit. So guys, here's what we know. How do you make a reaction go faster? Heat it up. That changes frequency and magnitude. Grind it up. That changes frequency. Or the last one is add more reactant, and that also changes frequency. You guys good? Okay, we're almost done. One more to go. Guys, there's one other way to make a reaction go faster. And it's this. Add a catalyst. Guys, when we do the lab on Monday, this will not be an option for you. The reaction that we're going to do does not have an appropriate catalyst, but we can talk about it anyway. So guys, a catalyst is a substance that speeds up a reaction without being consumed during the reaction. It's the magic stuff that they put in the hot pack that makes the iron rust more quickly. By the way, guys, why did they grind up the iron in the hot pack? Surface area. It's almost like we're learning stuff. I think what they should do is just put a big old chunk of iron in there. It wouldn't work as well. So guys, here's the thing that's interesting. We now know right now that to make a reaction go faster, you've got to either increase the frequency or the magnitude of the collisions. So guys, with a catalyst, do catalysts increase the frequency or the magnitude? And guys, the answer is neither. This is important to understand. Guys, catalysts do not increase the frequency or the magnitude of the collisions. So guys, if that's true, what does a catalyst do to get more collisions over the hump? Go ahead. Beautiful. Guys, it drops the hump. It literally drops the hump between reactants and products. Nice work. Yep. How does it do that? Guess what I'm going to tell you? No. We talk about it in AP. Sorry. I know. But it's really cool. It's fascinating. It almost feels like witchcraft. It's really neat. So guys, this then is what I need you to do. Go back to your reaction diagram and draw in a new pathway. That red line that connects reactants to products. Guys, draw in a new pathway where there's a catalyst present. What would that look like? Predict and then draw what that might look like. So guys, did you draw something that looks like this? This is the difference. When we have a catalyst, you notice the reactants and products stay in the same place. The difference is the hump drops. And as a result, the collisions that are already happening, more of them can get over the hump. You guys good? How are we doing? Y'all caught up? Almost, yeah. How about now? Okay, so guys, we're going to wrap up the day in the next 2 minutes. But again, as you're working on the homework tonight, or even right now, you're going to have some time, be thinking about Monday. Because in Monday, you're going to go into lab and you're going to measure how fast a reaction goes. The way that we do this is really fascinating. But then you're going to do the reaction 3 more times and you're going to make it go faster. Be thinking about how you might do that. And then when you get together in lab on Monday, you and your lab partner are going to sit down and you're going to talk about it. What can we do to get this reaction to go faster? Just a second. I don't want to talk about it now because I don't want to give you, I want you to think about it. But guys, as advertised, we now need to come back to our introductory question. Why? Why does the burning log go so much faster than the rusting iron? Guys, just like before, take a second and talk with the person next to you about it. Why do they go faster? It's funny, guys, all the answers are running through my head, and I'm like, oh my gosh, we could talk about this for an hour, but we're not going to. All right, guys, let's pull this together and let's see what we know. Again, the question is, why does the reaction on the left go faster? Tori, go ahead. Good. So, guys, this reaction is releasing energy. So much more energy than this one. And some of that energy cycles backwards and accelerates the oxygen and the wood particles. And so they're hitting harder and more frequently. So that one's hotter, and hotter is faster. What else? Go ahead, Rhett. You do. You have a greater amount of the wood. Absolutely. Yep. What else? Jessica. Why? Okay, so what's happening here that causes that not to be the case? How come? Because it's hotter. Absolutely. Ryan, go ahead. Oh, yeah. There's other thoughts. Go ahead. Just a second. Good for you. There's definitely more surface area there. So not just concentration, but surface area. I'm going to say, Sam, I think I know what you're going to say, and I want you to hold it for a second, because this is other ideas. All right, Sam, what else? You said it earlier, kind of welched a minute ago. You remember? So guys, what about activation energy? Which one has a greater activation energy? Not quite. It takes the same amount of energy. It just has more energy to use. But guys, which one do you think has a higher activation energy? The slower rusting or the faster burning? And guys, it's actually true. If you draw in the activation energy humps for these, the activation energy hump for the iron is much, much greater. So the question is why? Well, guys, think about the bonds that exist inside of iron. It's iron. They are so tightly bound together that it's hard to get them to break apart and rust. But guys, the bonds that are in wood, the cellulose, are much weaker, they're easier to break, and therefore the activation energy is lower. So guys, this has a lower activation energy, so it's got a lower hump, and it's got all the other stuff that you talked about with heat and surface area and concentration. And that one goes bonkers, and this one's chilling for centuries. Do you see the differences between the two? Guys, that's fascinating to me. So, gang, you've got a little homework to look at over the next couple days. Looking at the homework packet, it is assignment number 2. It is a couple pages long. It's all qualitative in nature. The beginning of it is terms. The second part of it is, frankly, a setup for the lab. And then, guys, the rest of it is just your opportunity to think through the things that we learned today. So guys, before midnight tonight, please record the acid-base homework, assuming that you did it and got your questions answered. If you're taking the replacement test, that is today, right after school, not after lunch. And then guys, finally, this homework we will talk about on Monday, and then we'll do a lab on Monday. I love this time of year. Yeah. Yes, good for you. Temperature is the only one that increases magnitude. Frequency as well, but it's the only one that increases magnitude. Yep. Although stirring kind of does a little bit too, but we're not counting it. Okay, so you guys good? All right, go get them. Let's work on some of this homework before we go.